In this lesson, we are going to look at the relationship between Mach number, True Airspeed or TAS, and Calibrated Airspeed or CAS, and why it is relevant to the operation of our aircraft. To conclude the lesson, we will look at the combined Mach airspeed indicator and the errors the Mach airspeed indicator is subject to. Let's begin then by considering what will happen to the Mach number and the TAS as an aircraft climbs in the standard ISA atmosphere at a constant CAS. The best way to show this is to create a graph. Looking at the graph, we can see that if the climb is carried out at a constant CAS, the TAS will increase with altitude, and the Mach number will increase even more than the TAS. If we think about it, we can see why this happens. Let's go over our graph again. The density of air changes with temperature and pressure, and will therefore vary with altitude. If a constant CAS is maintained during a climb in the standard atmosphere as air density and temperature decrease, the TAS will increase. The speed of sound, on the other hand, will decrease. However, the Mach number is a ratio of the TAS to the local speed of sound, and therefore the Mach number increases proportionally. So, if an aircraft was to be flown throughout the climb at a constant CAS, it would be quite possible that the aircraft could exceed Mach number limits as altitude is gained. High-performance aircraft are flown at a constant CAS, or indicated airspeed, for the first part of the climb, and the remainder of the climb is flown at a constant Mach number. Let's now see what happens if we descend in the standard ISA atmosphere at a constant Mach number. In the descent, the temperature will be increasing, and so the LSS will be increasing. Remember, the Mach number is the ratio of the TAS to the local speed of sound. Therefore, if the Mach number is to remain constant, the TAS must increase. The air density is also increasing in the descent, therefore the CAS must increase. Pressure change has a greater effect on air density than temperature change, therefore the CAS will increase at a greater rate than the TAS. The best way to see this is to put an actual example on the graph. If we say that at 40,000 feet the Mach number is 0.8 m, the calculated TAS will be 450 knots in the standard ISA atmosphere. In a constant descent at 0.8 m, the TAS will increase to 528 knots at sea level, which may well be in excess of the maximum normal operating speed for the aircraft. CAS is used in the lower part of the descent. Note from the graph that although the constant in this example has been the Mach number, the relationship, and therefore the sequence, of CAS, TAS and Mach number has remained the same as for a climb at a constant CAS. In the international standard atmosphere, the sequence will always be CAS, TAS and Mach number. A useful way to recall the sequence is to remember the letters CTM, or the mnemonic Chicken Tikka Masala. So far, we have only looked at the Mach TAS-CAS relationship which occurs in the International Standard Atmosphere, or ISA. So what happens if the atmospheric conditions do not follow the conditions assumed in the International Standard Atmosphere? To answer this, let's climb at a constant Mach number, and let's say we are climbing through an atmospheric inversion. In an inversion, the temperature of the air will increase as altitude increases. Therefore, in the climb, the local speed of sound will increase, and because the Mach number is the ratio of TAS to the local speed of sound, the TAS must also increase if the Mach number is to remain constant. Now, let's look at what's happening to the CAS. Calibrated airspeed, or CAS, when corrected for air density, gives us TAS. The air density is reducing with altitude, and therefore the CAS will be reducing also. In the descent, the reverse will apply. The LSS and TAS will decrease, and the CAS will increase. Note the Mach TAS-CAS relationship is no longer CTM, because ISA conditions no longer apply. Suppose our aircraft now has to climb through an isothermal layer at a constant Mach number. An isothermal layer is a layer of air where the temperature of the air does not change with altitude, so applying the same logic we applied to the inversion, let's see what will happen to the CAS, TAS and Mach number relationship. We know the temperature of the air will not change. Therefore, the LSS will not change, and neither will the TAS, if the Mach number is to remain constant. The CAS will change, however, as the air density changes. The density relationship between TAS and CAS means that as altitude is gained, if the TAS remains constant, the CAS must decrease. The CAS will therefore reduce in the climb. In the descent, the reverse will apply. Finally, we'll look at the Mach airspeed indicator. As the name suggests, the Mach airspeed indicator combines the function of an airspeed indicator, or ASI, and a Machmeter into a single instrument. There are two basic types of Mach airspeed indicators. In older aircraft, the Mach airspeed indicator is often a mechanical instrument which is fed from pitot-static sources to give an airspeed readout and a Mach number. We can see an example of this type of instrument here. The speed limiter pointer, or VMO pointer, is set manually, in the case of our example here, to Mach 0.75. The VMO pointer is commonly known as the barber's pole because of the diagonal stripe marking. As the aircraft accelerates, the airspeed pointer registers the increase in airspeed on a fixed scale, while the Mach number scale rotates to show the proportional increase in Mach number. The second type of Mach airspeed indicator is an electronic instrument, which uses information from an air data computer to display the Mach number and airspeed in digital form. We can see a typical example here. The VMO pointer is commonly known as the barber's pole because of the diagonal stripe marking. High-speed aircraft are limited to a maximum operating speed. The maximum operating Mach number is known as MMO. The maximum operating speed is known as VMO. Where the Mach airspeed indicator uses pitot-static sources, the basic principles of both the airspeed indicator and the Machmeter still apply, and the combined instrument will have the errors of both the Machmeter and the airspeed indicator. These errors are firstly, instrument error. This error results from manufacturing imperfections, friction, and play in the moving parts of the instrument. The next error is position or pressure error, which occurs as a result of suction and turbulent airflow in the vicinity of the pitot head or static source. And thirdly, we have maneuver-induced error. This error results from temporary and unpredictable fluctuations of air pressure around the static source. Although the Machmeter does not suffer from density error or compressibility error, the airspeed indicator does, and therefore we have to consider these errors as well. Density error occurs because the airspeed indicator is actually reading dynamic pressure, which is displayed as airspeed. Therefore, the airspeed displayed will only be the true airspeed, or TAS, at the air density for which the airspeed indicator is calibrated. At airspeeds other than this density, the airspeed indicator will not indicate the true airspeed. Lastly, we have compressibility error. At high airspeeds, particularly above 300 knots, the air compresses when brought to rest in a pitot pressure sensing system. Consequently, the pressure sensed will be artificially high, which will cause the airspeed indicator to overread. Near the speed of sound, this error can be more than 20 knots. This concludes the lesson. A short summary of the main points of the lesson follows. Here are the main points of the lesson. In a climb in ISA at a constant CAS, the TAS will increase. Mach number will increase more than the TAS. High-performance aircraft are flown at a constant CAS, or indicated airspeed, for the first part of the climb, and the remainder of the climb is flown at a constant Mach number. In the descent in ISA at a constant Mach number, the TAS will increase and the CAS will increase at a greater rate than the TAS. In the ISA, the climb-descend sequence will always be CAS, TAS, Mach number. Remember CTM. In an inversion, the temperature of the air will increase as altitude increases. Pressure change has a greater effect on air density than temperature change. Climbing through an inversion at a constant Mach number, the TAS increases. The CAS decreases. Descending through an inversion at a constant Mach number, the TAS decreases. CAS increases. An isothermal layer is a layer of air where the temperature of the air does not change with altitude. Climbing through an isothermal layer at a constant Mach number, the LSS and the TAS will not change. CAS decreases. The Mach airspeed indicator combines the function of an airspeed indicator and a Machmeter into a single instrument. There are two types of Mach airspeed indicator. One type is fed from the pitot-static system. The second type is fed from an air data computer. High-speed aircraft are limited to a maximum operating Mach number known as MMO. The maximum operating speed is known as VMO. The errors which apply to a Mach airspeed indicator fed from a pitot-static source are 1. Instrument error. 2. Position or pressure error. 3. Maneuver-induced error. The airspeed indicator suffers from density error and compressibility error. The Machmeter does not suffer from density error or compressibility error.